And to understand the Raptor 3, one must first accept a terrifying premise. A rocket engine is a device designed to facilitate a continuous, catastrophic explosion while simultaneously preventing that explosion from destroying the device itself. In the previous section, we examined the plumbing, the pumps, the pipes, and the nozzle. But the plumbing is merely the stage. The performance itself is a chemical drama of such intensity that it pushes the very limits of molecular physics. And in common parlance, we say a rocket burns fuel. This is a polite understatement. A campfire burns, a candle burns. These are diffusion-controlled processes where fuel and oxygen meet lazily at a boundary layer, governed by the slow hand of atmospheric pressure and natural convection. A rocket engine, by contrast, is a high-pressure chemical reactor. It does not burn in the way we understand it. It undergoes a sustained, directed detonation that is throttled and channeled to perform mechanical work. In the chemistry of power beyond the campfire, in a standard terrestrial fire, such as a wood-burning hearth, the rate of energy release is limited by the availability of oxygen. As the wood heats up, it undergoes pyrolysis, releasing flammable gases. These gases rise and mix with the surrounding air. Because the air is only 21% oxygen and 78% inert nitrogen, the reaction is diluted. The nitrogen acts as a thermal sponge, absorbing heat without contributing to the reaction, which keeps the flame temperature relatively low, usually around 600 degrees Celsius to 1000 degrees Celsius. And in the combustion chamber of the Raptor 3, there is no dilution. By using pure liquid oxygen, or LOX, instead of ambient air, the engine removes the lazy nitrogen from the equation. This allows for a stoichiometric reaction, a perfect chemical balance, where every molecule of fuel finds its corresponding molecules of oxidizer instantly. When liquid methane, CH4, meets liquid oxygen, O2, in the high-pressure environment of the Raptor's heart, the resulting chemical reorganization releases energy at a density that is orders of magnitude higher than any terrestrial fire. And the reaction is simple in high school chemistry terms. NCH4 plus 2O2 leads to CO2 plus 2H2O plus energy. But in the Raptor 3, this reaction occurs at pressures exceeding 300 atmospheres. At these pressures, the gases are so dense they behave more like fluids, and the energy release per cubic centimeter is enough to vaporize the very steel containing it in a fraction of a second. In the blacksmith's bellows, the role of the oxidizer, the fundamental challenge of spaceflight, is that space is a vacuum. This sounds like an obvious point, but its implications for combustion are profound. Every jet engine on Earth, from the prop on a Cessna to the massive turbofans on a Boeing 777, is a parasite. It breathes the environment, sucking in vast quantities of atmospheric oxygen to react with its onboard fuel. This makes jet engines highly efficient in terms of weight, as they only need to carry the fuel half of the chemical equation. And a rocket engine has no such luxury. It must be entirely self-contained. This is why a rocket is essentially a massive tank of oxidizer with a smaller tank of fuel attached. In the case of the Starship system, the liquid oxygen makes up roughly 75% to 80% of the total propellant mass. And to visualize why we need so much oxygen and why we must pump it in at such high pressures, consider the ancient technology of the blacksmith's bellows. A forge fire, left to its own devices, is hot enough to soften iron, but not necessarily to melt it efficiently for high-speed work. When the blacksmith pumps the bellows, they are forcing a greater volume of oxygen into the heart of the coals. This increases the reaction rate, the number of chemical collisions happening per second. The Raptor 3 turbopumps are the most powerful bellows ever built. By forcing oxygen into the combustion chamber at 5,000 plus psi, SpaceX is essentially overclocking the chemistry. They are cramming so many oxygen and methane molecules into a small space that the frequency of molecular collisions skyrockets. This results in a flame temperature that exceeds 3,300 degrees Celsius or 6,000 degrees Fahrenheit. For context, iron melts at 1,538 degrees Celsius. The fire inside the Raptor 3 is twice as hot as the melting point of the engine itself. And energy density? Why the choice of molecule matters in the world of professional rocketry. We are obsessed with energy density specifically. How much potential work is locked inside a kilogram of propellant? This is the specific energy of the fuel. However, for a rocket scientist, there is a second, equally important metric, energy density by volume. And if you want the most energy per kilogram, pure liquid hydrogen, LH2, is the undisputed king. It is a tiny, energetic molecule, but hydrogen is also incredibly fluffy, denoting low density. Using it requires massive, heavy tanks that create immense aerodynamic drag. On the other end of the spectrum is rocket-grade kerosene, or RP1, which is very dense and easy to handle but leaves behind coke carbon deposits that clog the engine's internal machinery, making reusability difficult. And the Raptor 3 utilizes liquid methane, LCH4, which represents a Goldilocks middle ground. Methane has a higher energy density than kerosene, but is far denser than hydrogen. More importantly for the chemistry of the Raptor, methane is clean. When it reacts with oxygen, it produces mostly water vapor and carbon dioxide. Unlike kerosene, it does not leave soot in the delicate internal cooling channels of the engine. And this chemical cleanliness is what allows the Raptor 3 to be a full-flow staged combustion engine. In this cycle, the fuel and oxidizer are partially burned in pre-burners to power the pumps before they ever reach the main combustion chamber. If you tried this with kerosene, the pre-burners would quickly choke on their own carbon exhaust. By choosing methane, SpaceX opted for a chemical path that prioritizes the health of the machine over the raw, brute force energy of hydrogen, enabling the rapid reusability that defines the Starship program. And the steady-state explosion, managing the chaos. How do you contain a 3,000 degrees Celsius explosion without the engine turning into a puddle of molten superalloy? The answer lies in the concept of the steady state. And in a grenade or a stick of dynamite, the combustion is unconfined and transient. The reaction moves through the material as a shockwave, releasing all its energy at once. In a rocket engine, we want that same energy release, but we want it to stay put. We want the explosion to happen here, in this specific 3D coordinate of the combustion chamber, and we want it to happen continuously for minutes at a time. And this is achieved through the injector plate. If you look at the top of the Raptor 3 combustion chamber, the dome, you would see a complex, 3D printed plate perforated with hundreds of tiny, precisely angled holes. This is the shower head of the gods. And the injector's job is to atomize the liquid propellants, turning them into a fine mist, and to ensure they mix in a very specific pattern. If the mixing is too slow, the engine is inefficient. If the mixing is too fast or uneven, you get combustion instability. And combustion instability is the ghost that haunts rocket engineers. It occurs when the pressure of the explosion pushes back against the flow of incoming fuel. This creates a feedback loop. A pressure wave hits the injector, momentarily stopping the flow of fuel. The flame flickers, the pressure drops, a massive surge of fuel rushes in, and the flame gulps the fuel and creates an even bigger pressure wave. Within milliseconds, these oscillations can reach frequencies that match the resonant frequency of the metal engine itself. The engine begins to scream, then vibrate, and finally it unpacks itself, which is aerospace slang for exploding into 1,000 pieces. And the Raptor 3 manages this through the sheer precision of its digital control and the physical geometry of its injectors. By maintaining a combustion chamber pressure of 350 bar, the engine operates in a regime where the propellants are supercritical, a state where the distinction between liquid and gas disappears. This allows for near-instantaneous mixing and a flame that is so stable it behaves less like a fire and more like a solid, glowing pillar of force. In the thermodynamics of thrust, turning heat into motion, the final act of the combustion process is the conversion of thermal energy into kinetic energy. Chemistry gives us the heat, but heat alone doesn't move a rocket. If you explode a bomb in the middle of a room, the gas expands in all directions, and the net movement is zero. And a rocket engine is a heat engine, much like the one in your car, but it operates on a different thermodynamic cycle. In the Raptor 3, the high-pressure gas created by the methane-oxygen reaction is desperate to expand. The combustion chamber walls prevent it from expanding sideways or upward. The only exit is the throat of the nozzle. And as the gas is forced through the narrow throat, its pressure drops and its velocity increases. This is the fundamental law of fluid dynamics at play. To maintain the same mass flow rate through a smaller opening, the fluid must move faster. Once the gas passes the throat and enters the expanding bell of the nozzle, it undergoes supersonic expansion. And here, the internal heat of the gas, the random, chaotic motion of molecules bouncing off each other, is converted into ordered motion, where all molecules move in the same direction, down. This is where the chemistry finally becomes propulsion. The directed explosion pushes against the top of the combustion chamber with millions of pounds of force, while the exhaust is thrown out the back at several kilometers per second. And according to Newton's third law, the rocket isn't pushing against the air or the ground. It is pushing against its own exhaust. The more energy we can extract from the chemical bonds of the methane, and the more efficiently we can aim that energy out of the nozzle, the more push we get per gram of fuel. And the engine, as a living organism, when you stand near a Raptor 3 during a test fire, you don't just hear the sound, you feel the texture of the combustion. It is a roar that occupies every frequency of the human ear and vibrates the very marrow of your bones. This is the sound of billions of chemical bonds being ripped apart every second. And to the graduate-level observer, the Raptor 3 is not just a piece of hardware. It is a high-pressure chemical equilibrium. It is a masterpiece of non-equilibrium thermodynamics, where the flow of energy is so vast that the standard rules of stable matter barely apply. The engine is alive in the sense that it maintains a delicate, homeostatic balance. It must stay hot enough to ensure total combustion, but cool enough to remain solid. It must maintain enough pressure to drive the pumps, but not so much that it bursts the chamber. And everything we have discussed, the stoichiometry, the oxidizer mass, the energy density, and the steady-state explosion is managed not by human hands, but by a digital brain that thinks in microseconds. The hardware provides the cage, and the chemistry provides the fire, but it is the software that choreographs the dance. And as we move from the violent chemistry of the flame to the silent logic that governs it, we must shift our focus from the what to the how. How does the engine know when it is about to vibrate itself to death? How does it balance the flow of two different cryogenic fluids to within a fraction of a percent? End section break. The transition from a chemical explosion to a controlled ascent is not merely a matter of physics. It is a triumph of information. In the next section, we will step inside the mind of the machine to see how thousands of lines of code translate the raw violence of combustion into the surgical precision of orbital insertion. N1.4 The digital logic of propulsion, an overview for the CS mind.